In this unit, we are going to talk about systems of linear equations, a little as a continuation of the unit of linear equations that you can consult. So, we are going to define what is a system of linear equations. We are going to define what it means to be an equivalent system and how we are going to use them. And for that, you must remember, as I have said, what is a linear equation and know how to solve a linear equation as such. So, the first thing, a little so that you remember, a linear equation is the equation of the form 2x plus 2y equals to 1. As you can see there, we have seen that it has infinite solutions, because if you remember, geometrically it is representing a line. Therefore, all the points of this line are the solution of the equation. We can also talk about nonlinear equations, as could be the equation 4x squared plus 4y squared equals to 1. That equation is nonlinear, and geometrically it is representing all the points of this circumference. Therefore, all of them are the solution of the equation and also have infinite solutions. When we talk about a system, it is a set formed by the two equations. That is, we are going to look for solutions that are common to both equations, that satisfy both the equation of the line and the equation of the circumference. What does that mean? Well, it means neither more nor less that we will look for the points that are intersection of both figures. In this case, we only have two. The point x0 equals to a half, this one here above, and the point x equals to a half equals to 0, which would be this 4-point intersection. As I have said, not all the points of the line satisfy the second equation, the equation of the circumference. Therefore, only these 2 points are the solution of the system. This is a bit so that you can see what it is to be a system of equations. Obviously, in this unit, we are only going to worry about the linear equations where both equations are linear specifically. So, in general, there are systems with one solution, others with many solutions, even infinite, and others that do not have a solution, and that we are also going to find for linear systems and nonlinear systems, obviously. In any case, solving a system is to find all its solutions, or to determine that it does not have any solution. So, as I have said, the system of linear equations is a set of equations where all of them are linear, all of them have the same unknowns, x1, x2, xn, and the numbers that multiply them, the a sub ij, are the ones that we will call coefficient of the system, the b sub I, which is not multiplying any of the unknowns, we will call them independent terms of the system. So, for example, what we have on the screen is a system with m equations, they're in total m equalities, and in unknowns x1, x2, xn. The coefficient and the independent terms, as they happened in equations, are all real numbers known. So, for example, we have infinity possibilities. For example, this first example that you have here has 3 equations and 4 unknowns, x, y, z, and t. It is not necessary that all the equations depend on all the unknowns, but the unknowns that appear are the same in the 3 equations. Then here we have a system with 3 equations and 4 unknowns. And we can find all the possibilities, that is, more equations than unknowns, equal number of equations than unknowns, and even less equations than unknowns. In this other case, we have 2 equations and 3 unknowns. And this other example here has exactly the same number of equations as unknowns. Well, this is what we call a linear equation system, and we are going to worry about solving it. So to solve it, we have to know what a solution is. We are going to call a solution of a linear equation system to any set of numbers, alpha 1, alpha 2, alpha n, real, that meet all the equations of the system, all of them, as we have seen in the example of the intersection between the line and the circumference. They have to meet all the equations so that it is a solution. So solving a system will be finding all its solutions or determining that it does not have a solution. If it was the case, then, as it happened in linear equations, it may be that a system has infinite solutions, it may have a single solution, or it may not have any. So, we are going to talk about a general solution of a system of linear equations as the set of all possible solutions of the same, while each of the solutions will be called a particular solution. Exactly the same concept as in linear equations. So, for example, the system 2x3y equal to 7 x2y equal to 8, formed by these two equations with two unknown quantities x and y, has a single solution. In this case, it is x equal to -10 and -9. Therefore, in this system, the general solution and the particular one coincide since the solution is unique. We have more examples. This other system, 2x minus 3y equal to 7, 2x minus 3y equal to 0, is a system that does not have a solution. As you can see, there is no value of x and y, so that if the first equation is fulfilled, the second one is fulfilled. It is impossible. That is why it does not have a solution. Or the system 2x 3y equal to 7, 4 6y equal to 14 is a system with infinite solutions. In this case, the general solution is given by a parameter alpha, any real number, and it is this expression that you have here. And each of the particular solutions, we would obtain it by giving values to that parameter alpha. If alpha is worth 5, x is worth 5, and y is worth 1. If alpha is worth 1, x is worth 1, and y is worth -5/3, etc., etc. As we have seen, there are different types of systems. So, according to the number of solutions that they have, they are classified as consistent systems if they have a solution, or inconsistent if they do not have a solution. And within those who have a solution, we will call a consistent and determined one who has a single solution, and a consistent and indeterminate one who has infinite solutions. Well, we are going to be interested not only in finding the solution, because in fact finding the solution, we already have the classification of the same, in case it has a solution, it does not have a solution, and how many solutions it has. For example, the ones we have seen previously, the first one of them, which had a single solution, if you remember, x equals to -10 equals to -9, is a determined consistent system, since it has a solution and it is the only one. The second one of them was an inconsistent system, since it did not have a solution. And the third one we have put was an indeterminate consistent system, since it had infinite solutions depending on, in this case, an alpha parameter or any real number. Well, we are going to be concerned about finding and classifying the solutions of the system. Then, for this, we are also going to talk about equivalent systems. Two systems are equivalent when they have exactly the same solutions. And what we are going to do is, from a system, we are going to try to build equivalent systems to solve them, or at least to know what kind of systems they are. So, how do we go from a system to an equivalent system? Using, as in linear equations, what is called equivalence transformations. So what are the ones we know? For example, transforming one or several equations into other equivalents. For example, the system x plus 2y equal to 6, 3x minus 5y equals to 7 is equivalent to the system 2x plus 4y equals to 12. 3x minus 5y equals to 7. Because we have transformed the first equation into an equivalent equation, a result of multiplying 2 times the whole equation. Then, that would be a way of building an equivalent system. Another way would be to clear off from an equation one of the unknowns and replace it with the others. For example, this same system is also equivalent to the system x equals to 6 minus 2y. As you can see, we have cleared off the x, and now we substitute it in the second equation. 3 times 6 minus 2y gives me 18 minus 6y minus 5y equals to 7, which would be the equation as a result of replacing x by 6 minus 2y. Well, this system is also equivalent to the outside, because it will have exactly the same solutions. And another option is to add to an equation the result of multiplying another by a non-null number. For example, this system would also be equivalent to the system x plus 2y equals to 6, 3x minus 5y equals to 7, and 4x minus 3y equals to 13, where I add this equation, which is the sum of the previous two. In fact, I could even eliminate one of the three, since with 2 of them it would be enough to determine the system, and it would be an equivalent system to the previous one. Then, the equivalence transformations are the ones we have seen here, and they serve us to solve linear equation systems. And they are the ones we are going to use to solve this type of linear equations. Therefore, we have seen what is a linear equation system, nothing of transcendent equations, nothing of b-square equations, only linear equations, and how to build equivalent systems to then use them to solve this type of systems.